Okay, so today what we want to do is we want to talk about a continuation of last class when we were talking about the numeric approximation of integrals and introduce you guys two methods of doing it. One was the trapezoidal method and one was the Simpson's rule. And for trapezoidal method, if you have an integral from a to b of f of x dx, it'll be approximate, and you can both are a numeric approximation, it'll be approximately delta x over 2 f of x naught plus 2f of x1. And you do that all the way to f of xn minus 1, twice of that, plus f of xn. So that's the trapezoidal rule. For Simpson's rule, here's delta x over 3 now, and I explained to you guys last class why. And integral from some fx naught plus 4fx1 plus 2fx2, and then you alternate between 4 and 2 all the way to the last one, which is going to be 4fxn minus 1 plus fxn. For this one, n has to be even. Has to be even number. If n is not even number, then you're not going to have the correct number of terms. And I explain why, because of the partitioning part. What happened was you were having, so if n is, for example, 3, 1, 2, 3, then you have these 3 will give you a curve, but then there is only these 2, not enough to build another parabola. So you need to have 3 partitioning or even number partitions to be able to create parabolas consecutively. Anyways, one of the applications of numeric approximation is in calculating logarithms. Now, I don't know how far back you guys can go, but in your introduction to mathematics, but at the time there was a what we call the logarithm tables, log tables, and they were in the back of some books that you could use or you could look them up, and they were just basically saying what's the natural log of some numbers. And it was just like, I don't know if you guys have seen also normal distribution in statistics. There's a table for it that you can use. It's usually in the back of the book. And they would just say what's log of 1, log of 2, log of 3, log of 4, log of 5, log of 6. So they would tell you the natural log of different. That's why we have log properties, to be able to calculate log of different base, because the tables only came with log of base e, natural log. They will come in log base 7, base 8, or base 2.5 or whatever. So we will have to use log table to calculate those and use the properties of log to calculate those other than the standard natural logarithms. Again, that's just a side story. But the question here is, can I calculate approximate, like say natural log of 4, for example? What's natural log of 4? Well, if you think about it a little bit carefully, you'll say, okay, that's natural log of 4 minus natural log of 1, because natural log of 1 is 0. And that's really integral from 1 to 401 over x dx. And the derivative of 1 over x is natural log. From 1 to 4 would be natural log of 4 minus natural log of 1. So I can use this to approximate natural log of 4, for example. So let's just say, let's use both methods. Let's say n is equal to 6. If I wanted to use a trapezoidal method, and again, let me just show you guys, this is 1, 2, 3, 4. If I use n equal to 6, and I intentionally pick that. So 1, 1.5, 2, 2.5, 3, 3.5, and 4. Trapezoidal method says, and delta x, of course, in this case is going to be 4 minus 1 over 6, which is 1/2. The trapezoidal method says this is approximately equal to delta x over 2 f of x naught, 2 f of x1, 2f of x2 2f of x3, x3 would be 5/2, 2f of x4, x4 is 3, 2f of x5, and f of x6. F of x1, f of x2, 2 times 2/3, 2 times 1/2. It's just reciprocal, right? 1 over x. 2 times 2/5, 2 times 1/3, 2 times 2/7, and 1/4. Again, remember your functions, f of x is 1 over x. So it just flips all the numbers. You go 1/4, 1 plus 4/3 plus 1 plus 4/5 plus 2/3 plus 4/7 plus 1/4. So you get 1/4, 1, 2, 4/3 and 2/3 is 6/3, which is 2. So 2 plus 2 is 4 plus 4/5 plus 4/7 plus 1/4. Now I can use a calculator for this. Of course, you could do this also as easily by hand, but I'm going to use a calculator for this. So 4 plus 4/5 plus 4/7 plus 1/4 times 1/4. So the value is 1.40535, and I'm going to write a few digits just so I can have a nice comparison here. Okay. Now, if I use Simpson's rule for this, same everything, I use Simpson's rule for this, I will get, first of all, am I allowed to use, do I have the correct setup for Simpson's rule for this? Well, n is supposed to be even. That's basically the main restriction, and n is even 6. So I should be able to do that. So it's going to be f of 1, 4 times f of 3/2, 2 times f of 2, 4 times f of 5/2, 2 times f of 3, 4 times f of 7/2, and f of 4. And all of that multiplied by delta x over 3, f of 1, 4 times f of 3/2, 2 times f of 4 times f of 5/2, 2 times f of 3, 4 times f of 7/2, f of 4. F again is 1 over the number, whatever it is. So you get 1/6, 1 over 1, plus 4 times 2 over 3, plus 2 times 1 over 2, plus 4 times 2 over 5, plus 2 times 1 over 3, plus 4 times 2 over 7, plus 1 over 4. Which is 1/6, 1 plus 8/3, plus 1 plus 8/5, plus 2/3, plus 8/7, plus 1/4. 1 plus 1 is 2, 8/3 and 2/3 is 10/3. Then you have 8/5, 8/7, and 1/4. Once again, I'm going to use my calculator and calculating these. So I have 2 plus 10/3 plus 8/5 plus 8/7 plus 1/4 divided by 6, of course, which I get 1.38 7698413. Again, going a little bit too far in my decimals. So this is an approximation of ln of 4. My trapezoidal rule was 1.40 1.405357143. That was this is trap, this is Simpson. I know symmetry too much today. Simpsons. And then the calculator tells you ln of 4 is equal to 1.3862943661. This is calculation based on your calculator. And you can see Simpson's rule is very sorry about that. This is Simpson. This is trap. As you can see, Simpson's rule is very close to the actual calculated value. Now that closeness, how close is your value to the actual value of a function? Now here we're using natural log, but that closeness can actually have a bound. So we have what we call error bounds for our numeric approximations of the integrals. Error bounds. Error bounds basically, if you think about it, it's like kind of like a marginal values or the margins of like, okay, you know how you do like surveys and they say, okay, 39% of people prefer coffee to tea, for example. And they say, well, the margin of error is 3%. So if they say 39% of people prefer coffee to tea and the margin of error is 3%, that means you can have anywhere between 39 minus 3 to 39 plus 3% as your actual value. So you could have anywhere between 36% to 42%. That's the error bound. Like the 3% is supposed to provide some kind of like an error. Like it could be off by 3 at most. So it could be a little bit 3% less than this or 30% more. Now this is a deeper discussion in statistics, but I'm trying to build some intuition here for what error bounds are. Error bounds basically are saying, well, these are the bounds for your how far off you can be from an actual answer based on, and they usually depend on your n value. The bigger n, obviously, you're going to get a better approximation. The smaller error bound, the smaller n value, you're going to have a little bit worse approximation, bigger error bound. Now, the bigger the error bound, of course, means you will have a less desirable approximation, and the smaller error bounds means you have a better tighter error around tighter bounds around your approximation, which means you're closer to the actual answer. So if somebody says plus minus 3%, that's a wider error bound to say plus minus 0.5%. Plus minus 0.5% would mean you're between 38.5 and 39.5. That's a pretty good, nice, a lot tighter bound than you would have if you have a bigger error bound. Like if it's a plus or minus 15. Now that gives you a really wide interval that value could fall in between, and that's not a very useful situation or approximation. So that's the idea behind error bounds. As I said, each of these numerical approximations have some error bounds. For example, the error bound for trapezoidal rule is K, and I explained to you guys what K is. B minus A, of course, B and A are the two endpoints of your interval, and n is the size of the partition, how many partitions you have. So you see, the bigger the n, the smaller the error bound will be, because the denominator gets bigger, the fraction gets smaller. Also, the bigger the difference between B and A is, then you have a bigger error in between them. So, sorry, you couldn't see this. My apologies. So that's error bound for trapezoidal rule. For Simpson's rule, again, we're not going to derive why these are the error bounds for each of those. We're just going to use them. In Simpson's rule, it will be between less than or equal to k. And again, the k here is different than the k here. I'll explain what the k is again. But b minus a to the, now in this case, you have a higher power for b minus a, so it plays a bigger role. And 180 n to the 4. And you have the size of the interval also plays. Again, here n is even. Okay. Now, what is k? K for the trapezoidal rule, k is the upper bound for your second derivative of function. And over that interval, of course, not everywhere, just over that interval. And then here, k is an upper bound for fourth derivative of the function. Now, you're like, well, how do I know that? Well, usually the functions you get is like one of the nice standard functions that you can see. Either they're like increasing functions or decreasing function after you take derivatives of them. So there is one of the endpoints will be your maximum value, or 1 over x, something like 1 over x, because if I take second derivative of 1 over x, I get 1 over x would be my function. My second derivative is negative 1 over x squared, and my second derivative would be 2 over x cubed, and between 1 and 4, the maximum value of this would be at 1, so it's always less than or equal to 2. If I take the absolute value of this. Between 1 and 4, again, I'm only looking at here. Now, if I want to calculate this, so my k would be 2. Any value bigger than 2 would work too, but 2 is the smallest of the values that I want to use. For the fourth derivative, if I do the third derivative would be negative 6 over x to the 4, and fourth derivative is 24 over x to the 5th. Once again, the highest value of it is at 1. So k equal to 24 for this problem, or any number bigger than that, but 24 is. As I said, you're going to get value, you're going to get functions that are easy to figure out which one is, what's the highest bound or highest value for your second derivative or fourth derivative. What's important to notice that as n goes, for the same n value, the error bound for Simpson's rule is a lot smaller, with n to the 4, than the error bound for trapezoidal rule. The midpoint rule, which we don't make a big fuss about it, is the same as trapezoidal rule, but instead of 12n squared, it's 24n squared. So that's it. So and midpoint and trapezoidal rule have similar error bounds. So going back to the example that I gave you guys for natural log, I know for trapezoidal rule k is equal to 2. So my bounds for trap would be 2 times, let me write it out for you. So going back to the example of 1 to 4, 1 over x dx, which is going to give you natural log of 2, natural log of 4. If I use trapezoidal rule, the error bound is going to be less than or equal to k, which I discussed as 2 for this particular function, b minus a to the 3rd power over 12n squared. So you get 2 times 3 cubed over, let's just write this as 4 times 3 for 12 because I want to cancel. 6 squared is 3 squared times 2 squared. So the 3 cube and the 2 3's cancel out. One of the 2's cancel out with 2, so I get 1 over 8. You could do all of this with calculator. I'm just trying to do things by hand a little bit. So now that's of course 0.125. Now, okay, so what does this mean? This is what it means. Now you see how when you use trapezoidal rule, You got 1.405357143. That means the actual integral, which is your ln of 4, is somewhere in between the trapezoidal approximation that you had, 1.405357143, either minus 0.125 or plus 0.125. So if I just do that calculation, I get between 1.2803574143 and 1.5303574143. And of course, the actual value, which was closer to 1.3862, does fall in between these two bounds. Obviously, the bounds are pretty tight, pretty wide. If I use Simpson's rule, though, error bound for Simpson's rule is now, if you remember the formula for it is K, but K, we decide K is, for Simpson's rule, is 24. So it's going to be 24 B minus A to the 5th over 180 N to the 4th, which is 24 3 to the 5th over 180 3 to the 4 times 2 to the 4. This and this cancel out, and 180 and one of the is 60. So it's 24 over 60 times 2 to the 4. To the 4 becomes 2 squared, this becomes 6. 6 and 6, again, you could do all these things by calculator, but you get 140. So the bound is 0.025. Which means, going back to what my Simpson's rule approximation was, which was 0.3876. So my ln of 4 with this approximation would be somewhere between what the Simpson's rule gave me, which is 1.3876984113 minus 0.025 and 1.3876984113 plus 0.025. So this one's going to be 1.36269818413, and if I added 1.412698413. I just added. And of course, the actual value based on the calculator is very close to 1.386. Sorry, my window is not very good today. I'm too close to the picture. So it's going to be between those two values. And 1.38 does fall right in between those two. So that's the idea of Simpson's rule and trapezoidal rule. Now, a lot of times the questions are ordered, like asked in a reverse order. In a way, they would say, hey, I want my error to be this. What should be my number of partition, the size of partition, if I want to have a certain error? So it doesn't say, given this size, find the error. It says, give me a size, the number of partitions that I need, so my error would be less than or equal to this. Okay, like for this particular example, for 1 over x, a question could say, find n. Question could say, find n for which natural log of 4 can be approximated within 10 to the negative 4 using a trapezoidal rule, the Simpson's rule. So I said, oh, for trapezoidal rule, I know it's my error bound is less than or equal to 2. I did the 2 is the k that we found out. 4 minus 1 to the third, 12. But the n that I'm looking for is n to the second power. And I want that to be less than or equal to 10 to the negative 4. For Simpson's rule, I would say the same thing. But now I would say 24, which is the k we found. 4 minus 1 to the fifth power. 180, once again, n that I don't know. And I want this to be less than or equal to 10 to the negative 4. So from here, I get 3 cubed times 2 over 12 n squared should be less than or equal to 1 over 10 to the 4. Or now I can cancel out 2 times 3 is 6, and then I have 9. 3 times 3 is 9. So I get 9 over 2, because 6 and 6 cancel out, n squared. So I could say 2n squared over 9 greater than or equal to 10 to the 4. You can always flip the two sides of inequality. Or 2n squared greater than or equal to 9, 10 to the 4. N squared greater than or equal to 9/2 times 10 to the 4. Then use your calculators for that. Or of course, n greater than or equal to 3 times 10 squared over 2. So I say 300 divided by root 2. I get 212.13. Because you want it to be greater than or equal to that, and you want whole numbers for your n. So n has to be 213 or more, because you have to have bigger than 212 and whole number, so 213. For Simpson's rule now, I have 24 times 3 to the 5th over 180 n to the 4 less than or equal to 1 over 10 to the 4. Or 180 n to the 4 over 24 times 3 to the 5th is greater than or equal to 10 to the 4. So if I wanted to purely use a calculator for this, I would say n to the 4 greater than or equal to 10 to the 4 times 24 times 3 to the 5th over 180. If I wouldn't just use calculator for that. So I would say That's going to be 10 to the 4 times 32.4. N has to be greater than or equal to 10 times 4th root of 32.4. Which is 2386. Now, for this, I have to go to the next number. Now it happens to be, say, input 24 then. It happens to be 24, which is an even number. Now, if this had turned out to be 22.86, you round it up, you get 23. 23 is an odd number. Simpson's rule requires an even number. So I have to go to the next number, which is 24. So you always go for Simpson's rule to the next higher even number. For trapezoidal rule, that's not an issue. And of course, look at this. If I want to have a certain error, trapezoidal rule requires like 213 size partition, whereas Simpson's rule only requires 24 partition. So the tables you see for the logs and for some trig functions and for normal distribution, your bell curve, those are all based on Simpson's rule. They're calculated using Simpson's rule. Has a better error bounds for same size partitions than either midpoint rule or trapezoidal rule. Again, your questions will not be anything beyond this. So the way I would be asking you is, I will give you an integral, I will give you an n, I will say use trapezoidal rule to calculate it or approximate it, use Simpson's rule to approximate it, or I would say figure out the error bound for each one. Or I would go the other way around. I would give you an integral. I will not give you an n, but I will give you a and a b. And I would ask you for what n I would get a certain level of accuracy. Your error bound would be less than or equal to something. So those are the two ways I would ask you. Okay. So I hope this kind of helped you or help clarify some of the questions in the homework. And look at the examples. You booked us examples like this, but with the different functions too. So that should be able to clarify things for you a little bit better. And of course, if it's not, then let me know and I can make another video for those. I thank you for paying attention to this, and I will see you guys or post another lecture. Next topic is improper integrals. So I hope you like that one. It's something that you use a lot later on as well. So it's good to have a correct understanding of it. All right, people. See you later.